in the second lecture of atmosphere, we will have more detailed um, investigation of the International Standard Atmosphere. Okay, so and we already know the International Standard Atmosphere is a standard atmosphere to define the conditions prevailing for most of the year for aircraft operating up to an altitude of 100,000 feet or about 30 kilometers in temperate latitudes. And that's, for example, the Europe and the North America. And usually we have this tabulated table of the ISA, and we there's some important parameters. For example, now I'm highlighting the sea level, so altitude zerometer. That's a sea level parameter, sea level pressure, and sea level temperature and density. So usually we need to remember these sea level parameters. Um, for example, the temperature is 101 kilopascal, and the temperature is 288 Kelvin, and the density is 1.225 kilogram per meter cube. Okay, and also we already know there are relative pressure, relative temperature, and a relative density, and the relative parameters are defined as the ratio between the local parameter divided by the parameter at sea level. And also we have the speed of sound, and the speed of sound is calculated as square root kRT. K is the 1.4 for air, R is a gas constant, T is local temperature. If we put the ISA table into graphs, it looks like this. And on the horizontal axis is different parameters: temperature, pressure, density, viscosity, and the speed of sound. On the vertical axis is the altitude. On the left-hand side is measured in meters. On the right-hand side is measured in feet. Okay, so let's first have a look at the pressure. It's highlighted in purple, and we can see it decreases continuously, and we know it decreases in an exponential way in the troposphere. So if we look at the temperature, and we know in the troposphere, and it decreases linearly until about 10 kilometer, and between 10 kilometer to 20 kilometers, and the temperature stays nearly the same. And then there's an increase in the until the tropopause, and then starts to decrease. The increase of the temperature in the troposphere is because of the UV light trapped by the atmosphere. So the temperature increases in the stratosphere. And so because of speed of sound is related with temperature, so it follows the same trend as the temperature. So we know the ISA model is a standardized set of reference parameters at different altitudes, but the local weather and the climate will influence the actual temperature and the pressure, and it will be different from the ISA temperature. For example, in here we have two graphs. It compares the local temperature across different time of the year. So we can see the dashed dotted lines are the ISA parameter, ISA temperature, and in different months and a different latitude, and we have different profiles, temperature profiles, but they are surrounding the ISA parameter. Okay, so this means also suggests the ISA parameter is kind of mean parameter, average parameter of the weather. So one important usage of the ISA table is for altitude measurement. So, and you can see the altitude can be measured by measuring pressure and use the ISA table to find the altitude. For example, we have ISA table, and let's have example. The pressure is measured to be 90 kilopascal on the top of a mountain. What's the height of the mountain? So if we have a look at the pressure on the mountain, it's 90 kilopascal. So it's between 750 meter and 1,000 meters. So then we need to do the interpolation. Okay, so if we use a linear interpolation like this, and a P1, we can use P1 as the pressure at H1, and the P2 is the pressure at H2, and then we can write H is the height of the mountain, write it explicitly, so we can use this formula. Then we just put in the numbers. We define H2 is 1,000 meter, and H1 is 750, and then P2 is P1 are the relative pressures, relevant pressures at different locations. So eventually we can have the altitude 781.35 meter. So we can see this is how we can make use of the ISA table to get the altitude